Hey everyone, and welcome to Deep Reinforcement Learning, Deep Learning in Python, Part 7. This course is all about the application of neural networks to reinforcement learning. If you've taken my first reinforcement learning class, then you know that reinforcement learning is on the bleeding edge of what we can do with AI. Specifically, the combination of deep learning with reinforcement learning has led to AlphaGo beating a world champion in the strategy game Go. It has led to self-driving cars, and it has led to machines that can play video games at a superhuman level. Reinforcement learning has been around since the 70s, but none of this has been possible until now. The world is changing at a very fast pace. The state of California is changing their regulations so that self-driving car companies can test their cars without a human in the car to supervise. We've seen that reinforcement learning is an entirely different kind of machine learning than supervised and unsupervised learning. Supervised and unsupervised learning algorithms are for analyzing and making predictions about data, whereas reinforcement learning is about training an agent to interact with an environment and maximize its reward. Of course, when it comes down to it, an agent sensing its environment is also data, but the way that it interacts with it is completely different. It's temporal, meaning that the data is treated as a sequence, and it's real-time, meaning that the agent acts in a way that affects the environment and hence it affects its next sensor readings. Unlike supervised and unsupervised machine learning algorithms, reinforcement learning agents have an impetus. They want to reach a goal. This is such a fascinating perspective. It can even make supervised and unsupervised learning seem boring in hindsight. Why train a neural network to learn about the data in a database when you can train a neural network to interact with the real world? While deep reinforcement learning and AI has a lot of potential, it also carries with it a huge risk. Bill Gates and Elon Musk have made public statements about some of the risks that AI poses to economic stability and even our existence. As we learned in my first reinforcement learning course, one of the main principles of training reinforcement learning agents is that there are unintended consequences when training an AI. AIs don't think like humans, and so they come up with novel and non-intuitive solutions to reach their goals, often in ways that surprise domain experts, humans who are the best at what they do. OpenAI is a non-profit founded by Elon Musk, Sam Altman, and others in order to ensure that AI progresses in a way that is beneficial rather than harmful. Part of the motivation behind OpenAI is the existential risk that AI poses to humans. They believe that open collaboration is one of the keys to mitigating this risk. One of the great things about OpenAI is that they have a platform called the OpenAI Gym, which we will be making heavy use of in this course. It allows anyone, anywhere in the world, to train their reinforcement learning agents in standard environments. One of the goals of my first reinforcement learning course was to set you up so that you'd be ready for the content in this course. At the same time, that course was massive by itself, so you can be sure that if you want to make sure you're ready for this course, there is a lot of prerequisite content you'll need to know and have experience with. In fact, I've dedicated an entire section of this course just to go over all the stuff you need to know and to review key principles. What else is in this course? After reviewing background fundamentals, we'll start building reinforcement learning agents for some select environments in the OpenAI Gym. This is a very different approach from my previous reinforcement learning course, where we built our own environments. I made the analogy that this was like playing a game in God mode, because we knew everything about the game and could look at its internals. Of course, it's not feasible to build all of our own environments. That would amount to building our own video games, which is a task that can take years for just one game and an entire team of people. OpenAI Gym gives us a super simple standard interface to all of its environments, so there's not much thinking we have to do beyond understanding how to interface with it. In this course, we'll be training an agent in the cart pole task, also known as the inverted pendulum. This is a reinforcement learning classic. The goal is to balance a pole on top of a cart for as long as possible. We'll be training an agent for the mountain car task. This is another reinforcement learning classic. The goal is to apply the right force at the right time to get the car to the top of the mountain. The car by itself can't generate enough force to push itself up the mountain in one go, so it has to use momentum to swing itself to the top. One key insight about these tasks is that if an agent can learn to solve them, it is essentially learning physics. If it can learn physics, it can learn how to move about physically in the real world. Here's an example of one of the robots from Boston Dynamics, so you know this stuff really works. There are already companies out there doing it. After we look at cart pole and mountain car, we'll look at one or more Atari games. Playing video games is an essential step we must take in order to build intelligent agents for the real world. Video games contain a larger set of actions than cart pole and mountain car, and the states don't necessarily reflect full knowledge about the environment. For example, look at this picture from the game Breakout. Can you tell whether the ball is moving toward the paddle or away? It's not clear because this is a static image, and that's all the information we get from a state. So we'll see that sequence modeling becomes important. But that's enough about what environments we'll be looking at. What about the techniques you'll be learning? In my previous reinforcement learning course, we learned about 3 main techniques for solving Markov decision processes, or MDPs. These were dynamic programming, Monte Carlo, and temporal difference learning. We learned that what we want to do eventually is solve what's called the control problem. That means learning the optimal policy so that whenever we're in a state, we take the best action based on that state. We learned that in order to find the optimal policy, one of the main ingredients is the optimal value function. We saw that by keeping a dictionary that maps states and actions to values, called a Q-table, we can eventually find the optimal policy by iteratively updating it based on experience. Then we saw that Q-tables aren't that useful because state spaces generally grow exponentially, and so we wouldn't be able to use them for anything but the smallest of games. We then looked at approximation methods which allow us to scale to large and possibly infinite state spaces. One key feature of the function approximators we use for reinforcement learning is that they are differentiable. In other words, we can train them using gradient descent, which you learned about in earlier deep learning courses. In my first reinforcement learning course, we stuck to linear models, but I stated that you could plug and play any kind of differentiable model, like a neural network. In this course, you'll learn that this is not necessarily the case. In fact, plugging in a deep neural network into the agents as we've been building them just won't work. You can get the syntax just right, and the neural network might appear to be approximating some function, but it just won't work as intended. In this course, we'll start by looking at RBF networks. These are old school, but they work well in reinforcement learning. They also fit into the context of what we did in the last course, and so they provide a good stepping stone to the more advanced topics in this course. After we learn how to build an RBF network, we'll extend our knowledge of temporal difference learning. So far we know about TD0, but we'll see how the idea behind TD0 can be extended to n-step methods and the more general TD lambda. After that, we'll look at a method that uses not one, but 2 function approximators at the same time. In particular, we'll be using one neural network to learn the value function, and one neural network to learn the policy. This is called the policy gradient method. Lastly, we'll look at deep Q-learning. At first glance, it might seem like we've already done this, deep learning and Q-learning together. But you'll recall one of my earlier statements was that you can't just plug and play deep neural networks into the agents we've built as is. It's just not stable enough. There are a lot of tricks that researchers have figured out that allow us to use deep neural networks in reinforcement learning agents. One of these tricks is experience replay, which I gave you a clue about in my last course. The idea is that as an agent plays an episode, it gathers a set of state, action, reward triples. These form a data set, just like the kind of data set you would use in supervised learning. So you don't necessarily need to do stochastic gradient descent like we did in the last course, where you only follow the gradient for one sample at a time, but rather you can calculate the gradient with respect to multiple previous samples. This helps stabilize the cost and hence the gradient. There are a lot of other tricks we'll need in order to make deep Q-learning work, but you'll just have to wait and see to learn what they are. I'll see you in the next lecture.